This is Chemical Reactions 9, which is about balancing redox reactions. And the overall goal of balancing redox reactions is to show the movement of electrons. We're going to use two different methods to balance redox reactions. We're going to use the net ionic equations method and the half reactions method. Now, you've done this experiment in lab. Here we have zinc that has been added to hydrochloric acid. So let's look at this single replacement reaction and write the net ionic equation. First, as you may recall, we're going to write and balance the reaction. So here we have our solid zinc, and when we balance it, we have 2 moles of hydrochloric acid to yield hydrogen gas in its diatomic form, along with zinc chloride in its aqueous form. Now, the next step is to write something called the complete or total ionic equation. Recall, in order to do this, you need to split any aqueous compounds into their ionized forms. You need to leave gases, liquids, and solids in their molecular form. So let's look at what that would be like with this reaction. Here, we're going to leave the zinc. We're going to split the acid because it is a strong acid that will completely dissociate. As you can see here, the coefficient in front of the hydrochloric acid is distributed between the hydrogen, so we have 2 hydrogen cations, and the chloride anions, so we have 2 chloride anions. That will yield the hydrogen gas, which we will leave in its diatomic form. However, the zinc chloride will ionize, so we have the 1 zinc cation. And also recall that this subscript becomes a coefficient. So we also have 2 chloride anions. Next, we're going to eliminate the spectator ions. So here we see that the 2 chloride anions occur on both sides of the reactions and thus are spectator ions. Next, we have our net ionic equation where we've eliminated the spectator ions, and this is our final net ionic equation. Now let's compare that to the half reactions method. First, you're going to assign oxidation states as you learned in earlier videos. Next, you're going to separate into half reactions. So you're going to have your reduction half and your oxidation half, and you're going to include electrons in these half reactions. So let's look at this half reaction in which the zinc is oxidized. So this is the oxidation half reaction. Then we have our reduction reaction in which the hydrogen cation is reduced. So this is our reduction half reaction. Next would be to balance for atoms and charge. In other words, we want to conserve mass, we want to conserve charge. We will balance charge by using electrons, and balancing atoms is what we've been doing throughout this entire unit. Okay, so what does this look like when we combine these reactions? Well, as you can see, if we take the reactants here, so we have our zinc plus our 2 hydrogen cations, and the charge is conserved. All right, so that means we can now eliminate that because it is balanced for charge, it is balanced for mass. Recombining these 2 half reactions into an overall reaction gives this final reaction. Now I want you to look at the 2 equations in red. They're identical. They're the same. So we can use either one of these methods when balancing redox reactions. Now, sometimes a half reaction has to have all of its coefficients multiplied by an integer. And this is done in order to have the electrons cancel out. In other words, to conserve the charge. Let's look at this reaction here in which a silver cation is being reduced, and then we have a copper being oxidized. So as you can see, atoms are balanced. However, the charge is not balanced. On the reduction half, we have 1 electron, and on the oxidation half reaction, we have 2 electrons. So what we're going to need to do is find that integer that we need to multiply through one of the equations. And in this case here, we're going to multiply the reduction half reaction by 2. And as you can see here, that's going to now give us 2 silver cations plus 2 electrons, and that'll yield 2 silver. All right, so we multiplied that all the way through. Now it's time to take our half reactions and combine them. All right, so when we do that, we have our reduction half, we have our oxidation half, and we can recombine those. Now I want you to note we have conserved charge. We accomplish that by multiplying the reduction reaction throughout by 2, and that will enable us to then cancel out the electrons, conserving charge, conserving mass as well. So our final redox reaction is as such, and as you can see, again, we've accomplished this by multiplying one of the reactions by some integer to enable us to conserve charge, and we've conserved mass as well. Let's go ahead and look at this reaction in which we have aluminum, and it is combining with a hydrogen cation to yield an aluminum cation along with diatomic hydrogen. Okay, so step 1 here, using the half reactions method. We're going to assign oxidation states. Let's go ahead and recall when assigning oxidation states to species, we have a set of rules that we're following. So here we have atoms in their elemental form, and we also have some monatomic ions as well. So assigning oxidation states here, we have aluminum in its elemental form is 0. Hydrogen is a monatomic ion plus 1. Aluminum, monatomic ion plus 3. Hydrogen gas, a diatomic elemental form with an oxidation state of 0. Step 2, we're going to take this reaction and we're going to separate it into its 2 half reactions. So what this looks like here, we have aluminum, and what's happening to aluminum? Well, in this case, aluminum is being oxidized, so this is the oxidation half reaction. It is being oxidized, and it is losing or giving off 3 electrons. Remember our mnemonics. We have Leo the lion goes grr, and we also have oil rig. Oxidation is loss of electrons, so it is losing 3 electrons. Now let's look at our reduction half reaction in which this hydrogen cation is being reduced into diatomic hydrogen. So when looking at this, you should see that we have an issue here with not only charge, but also mass. So we're going to need to look at that. We're going to need to balance the atoms or mass and the charge, and then ultimately combine these 2 half reactions. So for the second half reaction, you can see we have our diatomic hydrogen here. So there's 2 of them. So coming over here, we'll put a coefficient of 2 in front of the hydrogen cation. That's going to take care of the atoms or the mass. So we're conserving mass by balancing atoms on both sides. However, we still have an issue with the charge. So even when we put our 2 electrons there, because for each hydrogen cation, it's gaining 1 electron to produce a diatomic form of hydrogen gas. So as I previously mentioned, this is going to be one of those examples where we're going to need to multiply by some integer in order for electrons to cancel. I mean, we have 2 electrons on one side and we have 3 electrons on the other side. So as you may have surmised, we're going to take our top oxidation reaction and we're going to multiply it by an integer, and we're also going to have to multiply the reduction half reaction as well. We're going to make these both 6, so we're going to multiply the top reaction all the way through by 2. Now, sometimes students only do the electrons. You have to do the entire reaction all the way through when you're multiplying this out. We're going to multiply the reduction reaction all the way through by 3. And that's going to give us the following equations, which then we can recombine into our overall balanced redox reaction. So, looking at these, sometimes it's nice to situate them as you see here. It makes it pretty obvious in this case that we've successfully balanced for charge. We have 6 electrons being gained. We have 6 electrons being lost. And also we've conserved for mass by balancing the atoms on either side of this. So let's combine these into our final redox reaction, as you can see here. Now, let's look at net ionic. Let's look at example 2, where we have aqueous silver nitrate and it's being added to solid copper. Okay, first we're going to write and balance the chemical reaction. Silver nitrate, which is aqueous, plus solid copper yields. Well, this is a single replacement reaction. And remember that oftentimes we need to make sure the reaction will even recur. So let's look at the activity series of metals here. And indeed, you will see copper is just barely above the silver. Thus, it is more reactive. In other words, this reaction will occur and the copper will come in and basically kick out the silver in this single replacement reaction to yield copper 2 nitrate along with solid silver. So next we're going to go ahead and balance. Well, we have 1 nitrate here, but we have 2 nitrates here. So let's put a coefficient of 2 in front of the silver nitrate, which means we need a coefficient of 2 in front of the silver. Next, we can write out the ionic equation. And remember, this is the complete or total ionic equation. So again, note, solids, liquids, and gases do not ionize, so they are left alone. All the other species are broken into their cations and anions, respectively. Don't forget also that this coefficient multiplies through. So we have 2 silver cations, we have 2 nitrate anions. Over on this side here, we have 1 copper cation. However, this subscript becomes a coefficient, so we have 2 nitrate anions. Next, we're going to look for spectators on either side. As you can see, nitrate is a spectator ion, so we can cancel nitrate out, and we can write our net ionic equation. So, remember from the previous video, oxidizing agents and reducing agents. It's good practice to look at these. So in this case here, the silver cation is our oxidizing agent. It is being reduced. Because it is being reduced, it is causing another species, i.e. copper, to be oxidized. So the copper is the reducing agent. The copper is being oxidized, and because the copper is being oxidized, it is causing the other species to be reduced. And as you can see, the silver is reduced. Now, let's look at this equation and compare it to one we discussed earlier in this video. Take a look at this. You're going to see that they are identical. Again, we can use 2 different methods when balancing redox reactions, and they will give the same result. So, in example 3, we're going to look at aqueous copper 2 chloride when it is added to aqueous lead 2 nitrate. And that will form solid lead 2 chloride and aqueous copper 2 nitrate. Now, as you can see from this reaction, it is a double replacement reaction. There's a reason why I'm showing you this. So here we have our reactants, and they're going to produce the copper 2 nitrate along with the white crystalline precipitate, which is lead 2 chloride. looking to make sure we are balanced here. We have everything balanced in this reaction. Let's go ahead and skip right to the net ionic equation. So I'm skipping over the complete ionic equation, going right to the net. So I've eliminated spectator ions, and as you can see, we have the lead cation plus the chloride anions yielding this white crystalline precipitate, which is lead 2 chloride. Now, let's assign oxidation states to these species. Monatomic ion for the chloride, and then we have our precipitate. So the chloride is assigned a -1. However, there are 2 of them as indicated by this subscript. There are 2 chloride anions and 1 lead cation. So that means that the overall oxidation state for lead must be +2. Now, what you can hopefully see from this is there's no change in oxidation states. This is not an oxidation reduction reaction. This is an example of a metathesis reaction. In other words, no electrons are being transferred. And we can see that by using one of the methods, in this case the net ionic, to show we have lead 2+, and we're producing lead 2+. We have a chloride -1, and we're producing a chloride -1. So I wanted to show you this because there are not every reaction is a redox reaction. So I wanted you to remember that there are reactions that do occur that don't involve transference of electrons. Let's look at a couple more examples of redox reactions. Combustion. Combustion is an example of a redox reaction. So you can go through and assign oxidation states to these species. Recall that this is essentially a bookkeeping task, monitoring the movement of electrons within and among species. So in this case here, the combustion of methane yielding carbon dioxide and water, you can see that we can assign oxidation states to these species. Another example here that's really cool is this is a reaction that occurs in a lead acid battery. Lead acid batteries like the one in a vehicle. So that is the reaction that is occurring, and it is actually an example of electrochemistry, which is one of my favorite units in AP chemistry. So in this video, you've learned how oxidation and reduction reactions occur. You've learned about the net movement of electrons, and now you even know how to balance redox reactions using the net ionic equation method or the half reaction method. I'll see you guys in class.